Actually, I made a mistake because I think I left some issues that were not clear in my. So I would like to make a summary now because I want to make this concept fully clear to all of you. Okay? And in particular, one thing that I didn't make very clear is what happens if we change the versus of the force even by hydrodynamic forcing. So let's try to summarize by looking at the physical meaning, physical in terms of physics, at the physical meaning of what we did. We did an analysis of stability, where we assumed that there is a unit that is displaced on a side of a groin, and we assume that there are stabilizing and destabilizing forces. So, stabilizing forces is the weight of the unit, which has two components. One is perpendicular to the side, which is stabilizing. The other one is parallel to the side, which is destabilizing. Okay. And then we have another force, which is the hydrodynamic force. We assume it's a stabilizing force, but we also said it can be destabilizing. So what we did is to study the equilibrium of these forces. Why we studied the equilibrium? Because we are interested in the situation in which the stability of the unit is critical. And therefore, for this reason, we equated stabilizing and destabilizing forces. So what we did, let's step down, is to write this equilibrium relationship, which is reported here, where basically we put on the left-hand side the difference between hydrodynamic force and the component of the weight that is parallel to the side. And we took it positive C2 tau c d squared, which is hydrodynamic force. Positive because we assumed that this is stabilizing. And negative, the weight, because we assume that the weight is destabilizing because it tends to roll down along the side of the unit. Okay, and then we have the stabilizing force at the right-hand side. But let's say that C2 tau c d squared can be with the negative sign. Okay, so let's see what happens then. And then we develop the relationship that you see here, this one, where basically what happens if we put a negative sign here, we put a negative sign in the hydrodynamic force. What happens is that tangent beta becomes with the sign plus, okay, which is fine. I mean, it may happen. It may happen. This is okay. Let's say that it may happen. And then we said, okay, let's assume that beta is 0. And then we get to this relationship here. What happens if beta is not 0? And what happens if tangent beta here has a positive sign? What it happens is that the constant changes. So we have always this dimensionless number, which is equated to a constant. But the value of the constant changes if we assume that the hydrodynamic force is destabilizing and if we assume that weight is different from 0. But the conclusion doesn't change. The conclusion is that if you are able to estimate that constant, which depends on beta and depends on the fact, depends on whether or not we assume that the hydrodynamic force is stabilizing or destabilizing. But if we are able to estimate that constant, then our problem is solved. We have a dimensionless number that once it's known, basically gives to us the way, the means to estimate D, which is our unknown. Okay, now the problem is, first, what is the conclusion? Let me, from a conceptual point of view, the whole process depends from a dimensionless number, which is equated to a constant. Okay, now, the problem is that we recognize that to estimate the constant is difficult because it depends also on beta, it depends also on the versus of the hydrodynamic force, and we recognize that there is some, some assumptions behind which are not very reliable. Okay. Now, let's move forward by first saying one thing. If these assumptions are not met, so basically if we change the value of beta and we change the behavior of the hydrodynamic force, we recognize that the constant is no more a constant, meaning that the fact that we say there is only one dimensionless number governing the process, it's not true, because on the right-hand side, again, we have a constant that is not a constant. So, how can we develop a more refined analysis? How can we basically find an aid to estimate the value of that constant, which is not really constant because it depends on some parameters of the structure? Okay, one way, and this is the reason, the main reason why I wanted to introduce this conceptual reasoning, because one possible way of further inspecting this process is through dimensional analysis or Buckingham theorem. I'm quite sure that you heard about dimensional analysis already in your career, in your background. You have already some traces of dimensional analysis. I want to mention it because in coastal engineering, dimensional analysis is a tool that is frequently used. Dimensional analysis is an approach that allows us to investigate the dynamics of physical processes. What we have to do is to identify, for a given process, whatever, in this case is the process governing the stability of an armor unit. For a given process that we have to analyze, we have to identify the physical parameters that are effective. And we have to identify the units of these parameters. I'll go into the details. I'll tell you what are the parameters here that are effective. But you already have an understanding, like mass density of seawater, mass density, specific weight, which is the same thing, of the units, and beta, slope of the sides. This is an indication, but let's analyze them in detail later. Once that we have identified these physical parameters, we have to identify the units, how many they are. So, let me use the same symbols. Yeah. And yeah. Let's suppose that the physical parameters are in the number of n, as there is written there. Let's suppose that we have n physical parameters. Okay, and let's suppose that we identify for them k units. Typically, given that we are talking about the physical processes, they are three, which are L, M, and D. Length, mass, time. It can be proved, and this is the Buckingham theorem, it can be proved that then the process can be described by a number p equal to n minus k of dimensionless number. Dimensionless numbers. We don't prove this theorem. I hope if you had some background of applied mathematics, you already proved it, or mechanics in general. But this is what matters. It's also understandable by intuition. If you basically have physical and physical parameters that can be used to describe the process, and they depend on 3 units. If you make these parameters dimensionless by combining them, then it's understandable by intuition that you reduce your number of physical parameters to a reduced number, which is n number of physical parameters minus the number of the units. Okay, in this case, let's move forward, let's apply it here. What are the physical parameters? Let me read here because otherwise I forget something. So we have, let me see. Physical variables here are tau c, gamma s minus gamma, rho, mass density of seawater. And then we have d, characteristic shape of the unit, v, velocity of the fluid particles, so velocity of the waves. So basically these are 5. Of course, this is a tricky step. Identification of what are the physical parameters governing the process is a tricky step. If you forget something, your dimensionless analysis is not complete. And there is some subjectivity. For instance, you may decide that hydrodynamic force is not relevant, and therefore you forget one, which is V. So it depends on your evaluation of the process, your technical evaluation. You don't have to forget anything if you want to move forward in this way. Okay, let's identify the units. They are 3, mass, length, time. It means that Buckingham theorem says that the whole process depends on 2 dimensionless parameters, while our previous conclusion was just 1, the sheets parameter 1. But we recognized that this parameter is not constant. And if it is not constant, it means that we were missing something. So, what is the second dimensionless number that we can use to describe the process? So if we want to move further, if we want to remove that constant, which is not constant, and we want to put something more defined, what is the second dimensionless number? It can be proved that the second dimensionless number is the particle Reynolds number, which is indicated with RE star, usually sorry, I said RE and I wrote RF, RE star, which is equal to the product of something that is indicated with U star, which we will describe later, times D, we know what is, divided by the kinematic viscosity of water. Let me see that the symbols are the same. So, what is U star? It is the shear velocity, which is a characteristic parameter that we can express as the ratio, the square root of the ratio between tau and rho. Let me see if the symbols are coherent. Yeah. Rho is mass density of seawater, tau is friction. Friction can be estimated once that we know the wave behaviors. Okay, so what can we write? Before that, we wrote our relationship tau divided by gamma s minus gamma times d equal constant. This is what we wrote before. Then we can turn it into tau divided by gamma s minus gamma d is equal to a function of R E star. This can be proved through dimensional analysis. Now, what is the key message? The key message is, keep in mind that we don't discuss it more, but there is a tool called dimensional analysis, which allows you, through an analytical development, to derive a physical representation of the process you are investigating through dimensionless numbers. And this is complementary, confirms what we did by analyzing the equilibrium conditions. It must be complementary because we are doing the same thing with a different approach. The same thing is to analyze the stability of a unit with a different approach. With the first approach, I found the forces that are relevant and I studied their equilibrium. With the second approach, basically, I analyzed what are the physical parameters that are influential, and I found that they are related through this relationship. Well, still I have to define what is the shape of this function. If this is true, I should be able to verify it experimentally. And indeed, this was what Schitz did. Schitz operated in 1936. He proposed this relationship here in 1936. It's a relationship he worked in a flume envelope. But this relationship can be applied to verify any process where we are concerned about stability of rock units under the forcing of a flow current. Actually, what Schitz did was the opposite in terms of chronological order of development with respect to what I did. He started from experimentation, and then he found an analytical explanation through dimensional analysis. And this is what usually researchers in environmental sciences, in sciences in general, this is what researchers do. They identify a research question, they try to provide an explanation through reasoning and experimentation, and then once that they found an idea, they try to find a scientific explanation, physically based in this case, for it. So usually science starts from experimentation. We observe something which we don't understand, like climate is changing. We observe it, we get convinced, and try to understand why it's changing. Okay? In this case, what he observed, he made experiments in the flume, and he observed that units of segments at a certain point start moving. And he wanted to study the conditions in which a critical equilibrium was reached. Okay, and what he found is here. This is, I think, is one of the most interesting examples of experiments that were found for which it was found a critical physical explanation. Instead of looking at this diagram, which is barely understandable, let's look at another one. I put it in my web pages because this is public domain. This is the original diagram by Schitz. It's already public domain, and but it's barely readable. So let me open another one, and let me Google Schitz diagram, and let me turn to images. Okay, here. Okay, let me find another one. I think, okay, let me focus on this. It seems that this is, let me see if I can enlarge it. Okay, let's focus on, I don't like it very much. No, sorry, I don't like it. Because it's not easy to read. Let me find another one. Maybe one is better. Where is this?
But are we taking into account now that beta is still equal to 0?
No, absolutely not. Because, as I said, the fact that beta is different from 0 changes the value of your constant. And now, basically, we are sorry for that. We are studying the process with generality. And in this case, yeah, your comment is very good. Let me open this and then I give you the reply. Your comment is very good, I tell you. And let me open if I can enlarge this. No. Because this is nice. Okay. Okay, good. Okay, let me say. When we did this analysis of the physical parameters and the dimensional analysis, and we identified 5 of them, we didn't include the geometry, the beta, was not included. So given that beta is not included, it means that still Schiltz worked with the assumption that beta was close to 0. And in fact, in my lectures, in the following of the web page that we are taking into consideration today, you will find a correction of the constant for taking into account beta. So yes, your question was correct. We are still working under the assumption that beta is 0. And Schiltz worked under that assumption. And the reason is that he was interested mainly in river beds, where beta is close to 0. And in fact, as I said, we will introduce a correction factor. And if you take beta into account, that you increase the number of dimensionless number. So you have to basically introduce a correction, an additional dimensionless number. Okay.
I have another question.
Yeah.
Tau are different in the Reynolds number and the expression, right?
No. They are the same. It's the friction force is the same.
It's not the friction force between that one is between water particles.
No, this one is the friction exerted by water over the particle, which is the same thing as here.
Okay, it's not that one friction over the wall.
No. Basically, here you have a dimensionless number and another one here, but the shear velocity is computed by taking into account the friction force. The friction force that is exerted by a current of fluid over the perimeter of over the side, in this case, of the drawing. Is this clear? It's the same. Basically, the message is it's the same. Okay, so let's look at this diagram. What is this diagram? You see the shield in the vertical axis, in the y-axis, the Schiltz number, this one. And on the horizontal axis, you see the Reynolds number. So what did he find, Schiltz? He found that the Schiltz parameter, this one, it's not constant. So he put a cross here. And then he tried to understand the dependence on what kind of behavior it depends. He did probably a dimensional analysis, and then he proved in the lab and depicted here the dependence between the Schiltz parameter and the Reynolds star. And here you don't see the star, the symbol is different, but this is Reynolds star. What he found was that for high values of the Reynolds number, this is indeed the Schiltz parameter is constant. So basically this applies where there is a lot of turbulence for high value of the Reynolds star number. High values are reached when you increase the shear velocity. And the shear velocity is increased when you increase the friction factor, which means velocity of the waves. So he found that for high velocity, it's indeed constant. And for low velocities, low value of the Reynolds number, there is a behavior that is like that. And what is depicted here? It's depicted the relationship and the equilibrium between sheet parameter and Reynolds number. So the bold line, the thick line, identifies equilibrium conditions. So all the combinations of Schill's parameter and Reynolds number that are above the thick line means non-equilibrium, means instability. All the conditions that are below the thick line are stability. So basically, the conditions that are here, they are stable. And the combinations that you have above means no stability. And this is something that can be used to design. I mean, once that you know the tau, you can compute shear stress, and you can compute the Reynolds number for a given value. This is a physical parameter, it's a kinematic viscosity of water. You can compute for a given diameter the Reynolds number. So you can fix a diameter of the units, you compute the Reynolds number, and then you move here, and given tau, and given the diameter, you compute the Schill's number. And then you enter into the diagram, and you check whether the units are stable or not. If they are unstable, you increase the diameter. And then, if you increase the diameter, what happens? Okay, you have an increase of the Reynolds number, so you move in the right part of the diagram, but here you move in the lower part of the diagram, and then you get a stabilization. Okay, so if you were like here, for instance, in the first attempt, then you move to the right, and you move down, and you get to stability. When you design, what we do usually is to refer to turbulent conditions, and we get the value of the sheet parameter, 0.03. Okay, so given this number, 0.03, we can estimate directly. And then we check. We compute the Reynolds number and we check if we are indeed in this area here, or if it is too low, it's not good, because we get instability. It's very clear. Still, we have to correct for beta and for other issues. And also we have to estimate tau, which is quite okay. So let's try to go back to the lectures. And first of all, here there is an explanation on how to compute tau. And tau usually is made by two components. One is due to currents and one is due to waves. And here there is an explanation that I wanted to include here on how to compute, how to estimate this tau, depending on the characteristic of waves, and in particular depending on the significant wave height, which is defined in a way that you should already know. But let me say that what I want to know from you at the exam is up to here. So how to compute tau, this can be a question, and you should say, by considering a component due to waves and a component due to currents. And there are empirical formulations that allows us to estimate these two components if they are present, because currents may not be present in some conditions. And that's it. The reminder is something that I provided for your information. Okay. Effect of slope, very simple. We need to correct tau with a coefficient. That's it. Here there is detail, because you know the slope, it's not just one slope. We have a slope in the longitudinal direction and a slope in possibly, and a slope in the transversal direction. So this is why you see two angles here, two coefficients. But again, this is too detailed. I just need to know from you that to take into account the slope of the sides, we introduce a correction for tau, which is physically understandable. that's it. And then there is another issue. We consider an isolated unit, but usually units are not isolated, and they may have a shape like tripods that allows them to lock each other, okay? And then, again, a correction factor. Hiding and shape, correction factors. That's it. Okay, finally, this is something that I don't want to ask you, but I wanted to mention to you. This is the Hudson formula. It's self-explaining, and it's widely used, more than the Shields approach. So your question could be, why so you spent 1 hour talking about Shields, you could spend just 5 minutes presenting Hudson formula. The reason is that by looking at the Shields approach, I hope to have conveyed to you some key messages like how to analyze the process from a physical point of view, and how to make use of dimensionless analysis, which is extremely important, because when studying fluid mechanics and coastal processes in particular, you will find several other instances where you will find mention the dimensional analysis. So this is why I wanted to concentrate on Shields experience. I think that Shields experience is a very, very nice example of an experimental research that provided an extremely significant contribution for environmental management. He combined, again, lab experiments with dimensional analysis and his personal intuition to really provide a useful contribution. And I think it is nice to see that. But anyway, this is the Hudson formula, which is purely empirical, and I don't comment on it because it's really self-explaining. And just have a look. I'm not asking you to take exam. I may just ask you, are there alternatives? And you may say yes, for instance, Hudson formula. Okay, and that's it. Now, let's move towards the conclusion of our common experience, and let me go back to a final lecture that you see here, nature-based solution for coastal protection. Basically, this is an integration to structural measures. There are also what are called nature-based solutions. These solutions are today very popular for obvious reasons that we don't comment. And nature-based, I mean, they are less impacting, they don't make use of structures, and there is indeed one significant drawback. First, they are not so cheap, and if we want to make very good nature-based solutions, we need money. So sometimes they are considered to be cheap, but actually it's cheaper to displace a breakwater usually, rather than trying to stabilize the beach with the nature-based solution. And the second problem is that their effectiveness. Sometimes there is nothing to say other than the fact that they are less effective than structural protections, and for obvious reasons. But they remain an interesting topic. It's very descriptive what I'm proposing here, and I suggest you to have a look. I think it is, you see what are the solutions, besides this introduction of this diagram that is from Wikipedia, which is not relevant from a technical point of view. Cobble burns, meaning that you bring gravel on the beach in order to protect it. Strengths and weaknesses of the cobble beaches. Artificial dunes. There was a question by one of you, just I think it was you. So, you know, the dunes are natural shapes that protect the land. And when they are eroded, we can remake them. And here there is weaknesses. Beach nourishment, we talked with Gabriela yesterday, strength and weaknesses. Beach scrapping, what is beach scrapping? I already mentioned it to you. It means that the beach like of the Adriatic Sea, in order to prevent erosion of the beach during the winter, you scrape the sand and you bring the sand against the dune. You bring the sand back in order to avoid that it's brought away by the waves during winter. And then you redisplace the sand in spring, at the start of the touristic season. Strengths and weaknesses. Scraping is not exempted by weaknesses, and in particular you destroy the ecological environment of the beach, which is there. We don't see, we consider that beaches are like dead environments because there is the salt. It's not true. There is a lot of ecology there, and it's destroyed if you scrape it. Unfortunately, in order to understand that a beach is a very interesting ecological environment, we have to go in a place where the beach is not managed. And then we realize it. We realize that there are animals, there is vegetation, and if we compare with the status of the managed beaches, of the managed beach, we can really see the difference, and we understand the difference. Indeed, the managed beach often is dead. Because, you know, also the shells, they are removed, living organisms, they are removed because they are also dangerous sometimes. Dangerous, not really dangerous, but, you know, there are the kind of small animals that beat you. They are buried in the sand, and while you walk, they can beat your feet, and they are very, very painful. And so they try to remove everything to avoid this problem. And indeed, the managed beach is there. But if you look at a managed beach, you really understand what's going on. And then vegetation recovery. This is also very interesting. There are some pictures. This is an example where the dune is revegetated. And after a while, it becomes like